Welcome to AI Paper Slop, where we summarize the latest AI and tech papers for ML engineers and researchers. Today, we are jumping straight into a brand new paper called Reinforcement Learning with Evolving Rubrics as Rewards for Audio Reasoning.
Yeah, this one is from Fangsu Yu and a really massive joint team of researchers from UMD, UIUC, UIC, Microsoft Research, and MBZUAI.
Right. And to give you the core insights right up front, this paper introduces something called AUDIORUBRICS. It's basically a novel reinforcement learning framework designed to fix the bottlenecks in current reward models for large audio language models, or LMs.
Because right now, outcome-based rewards only check a model's final answer. And static process-based rewards eventually just saturate, they stop teaching the model anything new.
Exactly. So AUDIORUBRICS generates self-evolving per-sample grading rubrics directly from raw audio waveforms. It uses Gemini 3.1 Pro as an external judge to test these dynamic criteria against a policy model's own rollouts.
And that happens during group relative policy optimization, which we'll call GRPO. It mathematically prunes saturated metrics using variance filtering, which actively scales up the difficulty as the model learns.
Yeah, and when the researchers paired this evolving curriculum with an overthinking penalty, they optimized the Quen 2.5 Omni 7B model to achieve state-of-the-art results across major benchmarks. Like, it even outperformed massive proprietary models like GPT-4o audio.
It really represents a fundamental shift in how we supervise multimodal reasoning. To fully grasp what this is doing for you as an ML engineer, we have to look at why standard RLVR reinforcement learning with verifiable rewards is currently falling apart in the audio domain.
Right, because the dominant approach right now relies heavily on outcome-based methods. I mean, if you look at models like R1AQA or OmniR1, they're essentially trained to focus on a binary success metric.
Yeah, they only reward the final extracted answer at the very end of the reasoning chain.
Which seems intuitive at first glance, right? You give a model an audio clip, you ask it a multiple-choice question, and you just check if it picked option C.
It does seem intuitive, but in the audio domain, relying solely on that final output creates a massive supervisory loophole. LALMs are, they're incredibly adept at finding shortcuts.
Oh, absolutely. They'll just hallucinate the whole thing if you let them.
Exactly.
Yeah.
They can arrive at the correct final answer by hallucinating or by relying purely on text priors from the prompt without ever genuinely processing the acoustic evidence.
So if your prompt mentions a car crash, the model might just guess the sound of breaking glass based entirely on linguistic association.
Right. It completely bypasses the actual audio understanding, yet it still gets a positive reward because it guessed option C correctly.
So to counter that hallucination problem, the field started using process-based methods, right? Where instead of just grading the final answer, you grade the reasoning trace itself.
That was the idea, yeah. But the vulnerability there is that current process rewards rely on these really coarse, handcrafted static criteria.
Like a fixed checklist, stuff like, is the formatting correct? Or did the model output fluent text?
Exactly. And that static checklist is uniquely punishing in audio because audio is just fundamentally heterogeneous.
What do you mean by heterogeneous in this context?
Well, you have tasks that require simple zero-step perception. Think of just identifying the isolated sound of a doorbell. But then, in the exact same data set, you have tasks demanding complex multi-step inference.
Like figuring out a speaker's sarcasm based on subtle shifts in tone or background context.
Right. So a uniform, static rubric fails both extremes. For the doorbell sound, a complex rubric demands unnecessary reasoning. It practically invites the model to hallucinate details just to check the boxes.
But for the sarcasm example, that same static rubric isn't rigorous enough to enforce deep acoustic analysis.
Precisely. And this leads directly to the saturation effect.
Yeah.
As the policy model improves during the RL phase, it quickly learns how to reliably pass those fixed criteria.
And once it does that, the gradient basically vanishes, right?
Yeah, the training signal just saturates. The evaluation standards stop scaling with the model's growing capability, and your model simply plateaus, regardless of how much compute you throw at it.
We can contextualize this with a pretty straightforward analogy for the listeners. Relying exclusively on outcome-based rewards is kind of like evaluating a highly complex, multi-page calculus proof by only checking the final digit on the last page.
That's a great way to put it. You have absolutely no idea if the internal logic holds up or if the student just guessed correctly.
Right. And on the flip side, relying on static process rewards is like grading that exact same calculus proof using a primary school arithmetic rubric.
Yeah. Eventually, the student maxes out that basic rubric. They get a perfect score for formatting and basic addition, but they never actually improve their higher level calculus logic.
That framing perfectly captures the dual problem the authors are trying to solve here. So, to break out of that plateau, AUDIORUBRICS redesigns the evaluation pipeline from the very first step, before the GRPO loop even begins.
And the first critical architectural choice they make is how they ground the baseline. They completely discard the use of text transcripts for the evaluator. They go straight to the raw acoustic source.
This really stood out to me as a vital design choice. Before training kicks off, the system uses an audio-capable model. They selected Gemini 3.1 Pro 2, synthesized an initial set of 5 weighted rubrics for every single data sample in the training set.
And crucially, this generation is conditioned directly on the raw waveform as the native input. The absence of a text transcript here is non-negotiable for this framework.
Because if you feed an evaluator model a textual transcript, it falls right back into that text prior override trap.
Yeah, exactly. It will hallucinate audio cues based on what the text implies should be there, rather than what is actually audible.
So by forcing Gemini 3.1 Pro to listen to the raw waveform, they ensure the model's reward is strictly anchored to acoustic evidence that is physically present in the file.
Right. And let's look at what those 5 initial dimensions actually entail, because they are highly specific to audio processing.
Yeah, the system initializes with auditory evidence grounding, cross-key verification, reasoning clarity, reasoning focus, and domain-specific techniques.
So to put that into practice, imagine feeding the system an audio clip of a bustling city street with a faint siren in the background. The initial rubric for that specific sample isn't just asking, is the model's logic sound?
It generates a sample-specific criterion. Like it might ask, did the model specifically ground its reasoning in the Doppler effect of the siren peaking at 3 seconds into the clip?
Exactly. That sample-specific grounding is incredibly powerful.
But logically, a static rubric is still a static rubric, even if it was generated from raw audio. I mean, we just established that the model will eventually master these 5 specific points, the variance will drop, and the gradient will die.
Which brings us to the real core mechanism of the paper, the evolving rubric engine. This framework actively learns and adapts its own reward function dynamically during training.
So this dynamic evolution happens entirely inside the GRPO loop, right? Let's walk through exactly how a single iteration of that loop functions under AUDIORUBRICS.
Sure. So at each step, the policy model, which is the model you're actively training, samples a group of rollouts. In this paper, they use a group size of 8.
Meaning the model generates 8 different attempts at reasoning through the audio prompt.
Right. The judge model then evaluates those 8 rollouts against the retained rubrics from the previous step. But instead of just assigning a score and moving on, it analyzes those 8 rollouts to see where the stronger responses diverge from the weaker ones.
Oh, wow. So it's actively looking for the behavioral divergence.
Yes, and based on that divergence, it explicitly elicits up to 3 entirely new criteria. It acts like an active observant teacher.
So it looks at the model's current behavior and says something like, okay, half of these rollouts correctly identified the acoustic guitar and half confidently guessed electric guitar. What is the distinguishing acoustic feature the correct rollouts noticed?
Exactly. If the correct rollouts noted the sound of fingers sliding on nylon strings, the judge generates a new rubric demanding the identification of string friction. And importantly, these newly elicited criteria can be positive or negative.
Meaning the judge can write a rule that says, ensure you analyze string friction, or it can write a rule that says, do not rely on the presence of a drum beat to determine the instrument.
Right. You absolutely need those negative constraints to actively suppress recurring failure modes, like audio hallucinations that positively phrased rubrics just struggle to address.
But wait, I can spot the immediate computational problem here. If you elicit up to 3 new rubrics every single iteration, you're going to quickly end up with an infinitely growing list of criteria.
Yeah, the evaluation cost would skyrocket, and the reward signal would become completely hopelessly diluted. To solve this, the authors implement variance filtering.
Let's break down the math behind variance filtering because it feels like the engine keeping this entire system moving forward. For every single active rubric, the system computes the within-group standard deviation,
which they denote mathematically as S sub k. They compute that across those 8 rollouts. And the standard deviation is the key to understanding the health of your gradient.
So if S sub k evaluates to 0, it means there is absolutely no deviation among the 8 rollouts for that specific rubric.
Right. Every single rollout either perfectly passed the criterion or every single rollout completely failed it.
And if S sub k is 0, that rubric offers 0 group relative advantage. It's completely non-discriminative for the current state of the policy model.
Precisely. In a group relative framework, if a rule doesn't separate the good responses from the bad ones, it provides 0 useful signal for updating the model's weights.
The variance has vanished, so its utility as a teaching tool is exhausted.
Yeah.
So the system just immediately prunes it, right? It permanently removes that saturated rubric.
Yep. After pruning the useless criteria, it retains only the top M most discriminative criteria. For this framework, they set M to 5. It reassigns normalized weights to those 5 remaining rubrics and uses them to generate the final rubric reward.
Okay, I have to push back on this mechanism a bit because it sounds like it introduces a severe risk of catastrophic forgetting.
How so?
Well, if the model perfectly masters a specific behavior, say it gets exceptionally good at isolating background crowd noise from foreground speech, the variance for that skill drops to 0. If you throw away that rubric, you literally stop rewarding the model for doing it right.
That is a very valid concern.
So why wouldn't the model just unlearn that mastered skill if the system is no longer checking it?
To understand why catastrophic forgetting doesn't occur here, you have to look at the dual structure of the reward system. You still have the outcome reward anchoring the entire process.
So the system never stops checking the final multiple choice answer.
Exactly. That outcome reward acts as a hard boundary for final correctness, which prevents the model from losing its fundamental capabilities. The evolving process reward isn't designed to babysit skills the model has already mastered.
Its entire purpose is to act as a continuous escalating curriculum.
Right. By systematically dropping the easy mastered criteria, the system forces the mathematical gradient to focus entirely on the absolute edge of the model's current capability. It just keeps pulling the model continuously up the gradient.
That's fascinating. And the paper actually shows that by step 400 of the training process, roughly 60% of the active evaluation rubrics are newly evolved ones.
It proves the curriculum is successfully updating itself to match the model's growing intelligence.
You essentially build a shifting goalpost, optimized mathematically to keep the model in a state of maximum learning. But whenever you introduce a complex multi-tiered reward system in RL, you inevitably invite reward hacking.
Oh, absolutely. If the model realizes it receives a higher cumulative score for satisfying an increasingly nuanced list of rubric criteria, its natural mathematical incentive is to manipulate that reward.
Right. It does what any optimization algorithm would do. It attempts to harvest as many rubric points as possible, and the most efficient way for a language model to do that is to simply generate massive amounts of text.
Yeah, the paper includes a length dynamics graph that perfectly illustrates this phenomenon. Without any penalties in place, the model's reasoning trace just explodes.
It goes from a concise baseline of about 80 tokens and rockets up to over 400 tokens per response. The model starts generating extremely long, redundant, and circular logic.
It's essentially hoping to accidentally trigger every possible positive rubric condition just by sheer volume of output.
Right. And we should note the opposite extreme is equally problematic. If you completely strip away the process rubrics and rely entirely on vanilla GRPO with only outcome rewards, the reasoning length collapses in the other direction.
It drops to near 0 tokens. The model learns to just spit out terse, heavily under-reasoned guesses to get to the final answer as quickly as possible, and neither extreme represents genuine reasoning.
So to mathematically force the model to stay in the sweet spot between collapsing into silence and rambling infinitely, the authors introduce an overthinking penalty, which they denote as R sub over.
The formula for this penalty is remarkably elegant, really. It is defined as 1 minus the absolute value of O sub I divided by L.
And in this equation, the absolute value of O sub I represents the actual token length of the model's generated reasoning trace, right?
Yes, and L is a hard reference length limit, which the authors set to 256 tokens.
So by structuring it that way, you create a linear penalty that forces maximum efficiency. The closer the model's token count gets to that 256 token limit, the closer that division gets to 1, and the overall penalty term drops closer to 0.
Let's look at how that integrates into the final per rollout reward equilibrium. The final reward equation combines multiple weighted components. You have the accuracy and format rewards, which anchor the baseline output structure.
Then you add the dynamic rubric reward we've been discussing, which is weighted by a gamma parameter of 0.5.
Right. And finally, you subtract the overthinking penalty, weighted by a delta parameter of 0.15.
That specific calibration, adding the heavy rubric reward but pulling back with a carefully tuned length penalty, is what bounds the optimization problem. It mathematically forces the trace to remain incredibly informative and detailed while strictly limiting its length.
It perfectly prevents the zero-token collapse of vanilla GRPO while cutting off the infinite rambling caused by reward hacking.
The theoretical architecture is airtight, but the true test of any RL framework is its empirical performance. The team trained this entire pipeline using a dataset of 40,000 samples drawn from the AVQA dataset.
For context, AVQA stands for Audiovisual Question Answering. It provides a really highly diverse set of complex multimodal reasoning tasks, and they applied this training to the Quen 2.5 Omni 7B model.
The results against the established baselines are incredibly compelling. They evaluated the trained model across 3 major benchmarks: MMAU for multidiscipline audio understanding, MMAR for multimodal audio reasoning, and MMSU for speech understanding.
And across all 3, AUDIORUBRICS surpassed leading open-source models like Kimi Audio and Audio Flamingo 3.
But the real headline is that it consistently beat proprietary closed-source models like GPT-4o Audio and Gemini 3 Flash in several key metrics.
Yeah, while beating proprietary models is impressive, the most fascinating data point for an ML researcher is looking at where those gains actually occurred. On the MMSU speech understanding benchmark, the model's pure perception capabilities increased by 8.9% relative to the baselines.
I really want to highlight the implication of that 8.9% jump. It proves that enforcing a stricter, dynamically evolving standard for reasoning actually improves the model's fundamental ability to accurately perceive the raw audio.
Exactly. The framework isn't just teaching the model how to structure a logical argument better. The evolving rubrics are literally forcing the model's internal representations to listen more faithfully to the acoustic source.
To really internalize how this works in practice, we should look at the qualitative case studies they provided. The best illustration of this perception through reasoning effect is the Superman impression case study.
Yeah, this example perfectly crystallizes the failure modes of standard models. In the provided audio clip, a nephew asks his uncle to do an impression. The uncle groans and says, "No, not the kryptonite."
And the nephew immediately corrects him, saying, "That's Superman." The uncle responds with, "Thank you, I've been practicing a lot." The complex reasoning task here is to determine why the uncle said that final sentence.
When you run that clip through a baseline GRPO model, it completely fails. The baseline hears the lexically salient keyword Superman and immediately jumps to a superficial conclusion.
It guesses incorrectly that the uncle just wants to explain that he is imitating Superman. It essentially performs a basic keyword match and stops reasoning.
But the model trained with AUDIORUBRICS correctly deduces the complex underlying intent. Because it was trained under a rigorous, self-evolving process curriculum, it learned to map out the dialogue state chronologically.
It tracks the initial request, notes the specific impression attempt, registers the factual correction from the nephew, and then logically infers that the uncle mistakenly interpreted the correction as praise for his acting skills.
Right. It maps the subtle temporal flow of the conversation rather than just latching on to the loudest noun in the waveform.
Another really compelling case study is the Field versus Woods Acoustic Challenge, where the model has to accurately determine a physical location based entirely on ambient audio.
When the system initiates, the static rubrics generate a basic rule. They ask the judge to check for no water sounds to help rule out the ocean-based multiple choice options.
Which is a very basic zero-step perception task. But as the training progresses, the evolving rubric engine kicks in. The model generates its own dynamic rubrics that ask the judge to look for highly specific spatial acoustics.
It actively learns to interrogate the audio for the difference between the open resonance of a field and the dense, muffled acoustics of heavily wooded areas.
It learned entirely on its own to ask a significantly harder acoustic question to differentiate the remaining options. It's just a perfect demonstration of the variance filtering working exactly as intended.
It really is. However, this entire system has a highly sensitive single point of failure, which the authors expose in their ablation studies. They ran an experiment where they swapped out the highly capable Gemini 3.1 Pro Judge for a significantly weaker model GPT Audio 1.5.
And the moment they introduced the weaker judge, the overall performance of the model just plummeted. In fact, it dropped below the performance of the vanilla GRPO baseline that had no process rubrics at all.
Yeah, it demonstrates that the entire framework is intrinsically reliant on the judge model being highly capable of both evaluating subtle acoustic evidence and generating nuanced, grammatically precise criteria.
If your external judge hallucinates, or if it writes vague, poorly structured rubrics, it completely poisons the reward signal. The policy model will internalize those terrible habits, and the dynamic curriculum becomes actively destructive.
Which naturally raises a critical question for you if you're planning to implement this in your own pipelines. Does this evolving framework only function correctly if you have massive 7 billion parameter models acting as your policy model?
Right. Scale is always the big question.
Well, the paper confirms that the architecture is robust across different model scales. The researchers tested the exact same AUDIORUBRICS framework on a much smaller 3 billion parameter model, and they observed consistent relative improvements across the board.
Like the 3B model gained up to 3.65% on the MMSU benchmark, right?
Exactly. That is a vital takeaway. It proves that the high-quality signal generated by AUDIORUBRICS is robust across entirely different model capacities.
So even smaller, highly constrained models benefit massively from being held to a dynamically evolving standard, provided that the external judge generating those standards remains high quality.
For the ML engineers analyzing this paper, the practical takeaway is pretty clear. If you are fine-tuning multimodal models, relying on static process rewards is going to bottleneck your architecture. They inherently cap your model's potential by inducing gradient saturation.
Implementing dynamic, variance-filtered rubrics that are grounded strictly in raw sensory data and mathematically constrained by an overthinking penalty is the new state-of-the-art for eliciting deep reasoning.
You are no longer trying to handwrite the perfect static grading rubric for your dataset. You are building a localized ecosystem where the system learns how to grade itself in real time as it gets smarter.
It fundamentally shifts the burden of supervision from human intuition to algorithmic evolution, which leaves you with a deeply provocative implication to consider. If our multimodal models are now dynamically generating their own ever-evolving evaluation criteria, writing rules, standards, and negative constraints that human engineers never explicitly programmed, at what point does the model's internal definition of good reasoning begin to diverge from human logic?
That's the real question, isn't it?
Right. As these rubrics filter out zero-variance human concepts and evolve to capture harder and harder acoustic subtleties, are we eventually going to see them optimizing for a hyper-efficient alien acoustic processing language that we fundamentally cannot understand? You might be checking the final multiple-choice answer, only to realize the reasoning trace that got it there was optimized for an acoustic reality we can't even perceive. That's all for this deep dive into audio rubrics. We'll see you next time on AI Paper Slop.